Now, the biggest question in modern computing is scale. Scale up, scale out, and then be as efficient as possible. Every generation of computing has been defined by a single question: how do you scale? For decades, the answer was simple. We could simply build bigger chips and leverage the latest manufacturing node. But at advanced nodes, we know that this approach has started to break down. Power, yield, and cost have become real limits. The biggest chips in the world today now require more than what a single piece of silicon can deliver. That's where chiplets come in. Instead of one monolithic die, you build many smaller ones, with the idea that each of them is specialized and are easier to manufacture. By reusing chiplets to enable performance and scale, there are also cost and performance benefits too. You connect them together in a package. This idea isn't new, but when the interconnect becomes fast enough, coherent enough, and efficient enough, you can start treating multiple chiplets as one unified system. Now, that single shift has changed how the entire industry thinks about architecture. It's what has enabled AMD's EPYC processors, Intel's Foveros systems, and NVIDIA move forward towards modular GPUs. And it's opening the door to something even bigger, and we're starting to see architecture designed from day one to be composable at every level, from die to system to rack. That's where a new company I want to talk about called Tsavorite comes in. The companies I've mentioned before have started down the path of chiplets, but their approach rarely grasps the benefits of a truly modular approach. Tsavorite is building a coherent network of chiplets that act together, called Omniflexes, and are using different combinations of chiplets for different markets. This allows for rack-scale deployments with petabytes of unified memory through their new interconnect known as Multiplexus. The goal is simple: scale AI performance per watt from edge all the way to the data center with a composable system that can be both compute and memory optimized. I'm going to tell you how they do it. Before we dive deeper into chiplets and composability, I want to set the stage about the company we're talking about. Tsavorite is a new semiconductor startup based in California, with engineering centers in India and the US and more than 100 people already on staff. That staff includes expertise from Cisco, Marvell, Apple, Tesla, and many others. Now, it's one of the rare AI hardware startups that isn't chasing GPUs or accelerators. Instead, it's building complete compute systems with modular silicon that links CPUs, memory, and AI engines all together with a single coherent fabric. That's a roadmap that's designed to scale from small edge devices all the way up to the data center. The smallest designs focus on real-time physical AI, like robotics and sensor fusion, while the largest configurations target large-scale model training and inference. The idea is that they're all connected together, with the same set of chiplets and the same interconnect. That's what Tsavorite calls Multiplexus. We'll get into that later in the video. The company says its approach delivers up to 90% lower power and cost at the system level compared to conventional GPU clusters, while keeping full software compatibility through its own runtime stack. Now, it's early days. Silicon production ramps are planned for early next year, 26, but the technology is already up in FPGAs and running customer workloads. So the idea here isn't just simply another accelerator or a faster GPU. I could talk about a dozen companies doing exactly that. It's a unified compute architecture designed from day one to be modular, coherent, and scalable. To understand why that matters, we need to start about why actually chiplet economics work. To understand why chiplets matter, you have to look at the physics and the economics of manufacturing. Every time we move to a new process node, complexity and cost rises. As a result, the wafers that companies purchase from manufacturing fab companies like TSMC, Samsung, or Intel, they will cost more, and sometimes dramatically so. Depending on the deal that a company might have with, say, TSMC, or based on timing, partnerships, and volume, it's quoted that a 5nm wafer costs around $17,000 to $20,000, but the next generation of 3nm will be closer to $25,000. At 2nm, with new transistor technologies, it could exceed $25,000 to $30,000, even more. And by the time this video comes out, beyond that. It means that the number of chips you can pull from a single wafer, and the defect rate and yield of those chips, can determine the cost of your silicon. Today, we can build chips, single chips, up to 800 square millimeters, but a modern wafer will only manufacture about 64 of those, and most of them might not be usable in products. This comes down to the concept of defect rates, something we've covered before on the channel. Each defect has the potential to make a chip become unusable. Now, there are some tricks of the trade, but by and large, defects are a bad thing. As manufacturing node matures, defect density improves, but you still don't want that $2,000 reticle-sized chip to have a low yield rate. Chiplets, on the other hand, are designed to solve this. Even with the same defect rate, a smaller chip will have a higher yield. By enabling chiplets and connecting lots of the smaller chips together, it means you don't have to throw most of that wafer away. Now, if you can use that chiplet in multiple products, it changes the traditional mathematics and costs of production. You can build compute dies on a leading edge node, cache dies on a mid node, and I/O and memory controllers on something a bit more mature. Each part uses a process best suited to its function. And chiplets let you scale in multiple directions: more compute by adding tiles, more bandwidth by widening the interconnect, or more capacity by linking memory-rich dies. Now, on a personal note, I've been covering companies making chiplets for almost a decade now. The advances in interconnect and advanced packaging are making all of this possible. But realistically, few companies get the true purpose of chiplets. Ideally, you want chiplets that are the right size, but reusable across a wide product portfolio to amortize the cost and provide both scale and efficient performance from data center all the way down to the mini PC. I too often see companies make a small chiplet and it only goes into one product. The goal here should be to spread it around, but that also requires a coherent fabric. And that's where the real breakthrough lies, building that fabric to make any combination of those chiplets behave as one. That's where coherency, latency, and bandwidth matter most. Every company pursuing chiplets today is trying to solve that same challenge, to make multiple dies feel like a single chip. Now, making multiple chiplets behave as one system only works if the interconnect is fast, coherent, and scalable. That's usually where traditional architectures that we've been working on for decades hit a wall. Traditional fabrics, things like PCIe or UPI, were never designed for this. As a result, the industry has been working on updated fabrics, either using standard or custom physical layers with standard or custom protocol layers. Most fabrics aimed at high speed work well inside a single package, but they struggle to extend that coherence beyond it. Bandwidth falls off, latency rises, and memory stops feeling unified. So Tsavorite's answer is that thing I've already mentioned twice already, Multiplexus, and it's the backbone of everything they're building. The idea is that it's a distributed coherent fabric that scales across dies, packages, and even entire racks while maintaining a single memory space for all the chips to use. Each chiplet connected to Multiplexus can see and access the entire memory address space, allowing workloads to move seamlessly between compute and memory tiles without the constant copying or synchronization that usually kills performance. At its lowest level, Multiplexus operates as a high bandwidth, low latency network on chip with distributed caches. Within a package, it extends over UCIe, the Universal Chiplet Interconnect Express standard, to connect chiplets at near on-die speeds. Between packages, it extends that over high-speed SerDes links, preserving coherency even as systems scale up. Across systems and racks, it becomes a full inter-system fabric, a proper scale-up solution, linking chips into what Tsavorite calls unified memory pods. At the large scale, this can be petabytes of memory in one single unified memory space. Thing is, unified memory at this scale does come with its own problems. Maintaining global coherence is expensive, for example. Cache snoops can multiply quickly as you add nodes, and the cost of directory management can grow faster than the compute itself. Memory bandwidth becomes as much about control as it is about speed, and long-distance access across racks introduces non-uniform latency that software must either tolerate or hide. There are classic traps of large coherent domains. The architecture can look elegant on paper, but really fall apart if the coherence protocol or topology isn't designed to scale efficiency, and that's the part they claim to have solved. The result is a hierarchy that doesn't behave like a hierarchy. Where the data is on the same die, the same package, or a neighboring rack, Multiplexus is designed to manage the movement, coherence, and quality of service automatically. Thus, as the network scales, their tests have shown that the overall compute utilization actually increases because data no longer needs to be duplicated or relocated between devices. Now, for AI workloads, that's a huge deal. It means models with hundreds of billions of parameters can run in a single address space shared across chiplets that behave as one logical processor. Training, inference, and fine-tuning all benefit from that continuity. It's the difference between managing clusters and orchestrating a single distributed processor. Thing is, once you have a coherent fabric like Multiplexus in place, the next question is what you build on top of it. Tsavorite's answer is a family of chiplets that can both do compute and memory, but are optimized for different balances of the two. They call these Omniflex and Skyflex. Both are built from clusters of ARM Neoverse cores and their own AI cores operating alongside fast local memory. Omniflex is tuned solely towards higher compute density, whereas Skyflex is tuned towards capacity and bandwidth. It still executes compute workloads, Skyflex, but it carries a larger memory footprint and interfaces for external communications, and deals with models that might need to move large amounts of data between chiplets. Together, the idea is that they form a continuous design space. Every system that Tsavorite builds is some mix of Omniflex and Skyflex chiplets, collected through that multiplexus and managed by the same software stack. Now this slide shows how those combinations map through to Tsavorite system tiers, labeled T0 through to T3. Each tier targets a different scale of AI workload, from edge devices all the way up to data center training clusters. T0 here is the smallest configuration. It's using just 2 Skyflex tiles. It's designed for compact, low-power systems like embedded inference or real-time control. It's where Tsavorite's architecture starts, a small footprint, but still coherent and still unified. We're expecting to see this show up all the way from edge to mini PC and will be the cheapest variant aimed at inference. T1 steps that up into what the company calls physical AI. It's built for systems that need to process data from multiple sensors and run vision and mapping models at the same time and react. It combines one Omniflex chiplet with 8 Skyflex chiplets into a single package, scaling performance and bandwidth while maintaining low latency both between compute and memory. In terms of robotics, Tsavorite says that this single T1 chip will give 5 times the performance of NVIDIA's Thor platform today. That's their latest robotics-focused platform. T2 scales the same template into the data center. Each package has 2 Omniflex and 20 Skyflex chiplets, but from a system perspective, we're now looking at multiple packages or boards joined through Multiplexus. They all share the same address space, and Tsavorite claims that a T2 configuration can train a 70 billion parameter model on 15 trillion tokens in just over a day, roughly the scale of a small language model cluster, but operating within a singular unified memory domain. It's really interesting to see it positioned not only for inference but training as well. The same cluster, according to the company, can enable 360 million tokens per second of inference. That's a large number to believe, even for companies like NVIDIA, so I can't wait to see the testing data. At the top end is T3. This is the design that's scaling from multi-petaflop to multi-exaflop, built from many interconnected T3 chips. Tsavorite positions this against modern AI factory superclusters, claiming 3 times the token throughput and only 1/3 the power of NVIDIA's 2728 NVL rack, enabling 1/10 the cost of tokens. Again, that's a crazy bold number, but the architecture behind it, reusing the same Omniflex and Skyflex tiles as the edge stuff, that's what makes this scaling plausible. Now, Omniflex and Skyflex are 2 sides of the same silicon philosophy. Both handle compute and memory, but each are just optimized differently, and both are designed to scale coherently across the same fabric. It's this composable approach that sets up the hardware for Tsavorite's Helix systems, where these tiles become full products first. Once those chiplets are proven, the next step is these compute systems. That's where Tsavorite's Helix platforms come in. The first launch from Tsavorite will be in the form of Helix M, Helix D, and Helix R. Each one uses the same fundamental building blocks, the same fabric, and the same software, but scales them to different performance environments. Helix M is the smallest of the 3, where M stands for mini. It's designed as a single processor module for embedded and workstation class AI. It uses just one T0 chip, delivering full AI compute in that compact footprint. This is positioned as a small form system for local inference, robotics, or even edge data capture. And despite its size, it retains unified memory and full coherence across its internal chiplets, making it effectively a miniature AI computer. We've had a few of those recently. Helix D is the desktop configuration, multiple chips on a board working together as one system. It's aimed at the higher-end edge servers or development workstations where performance density matters, but density infrastructure isn't required. Each chip, as we've covered, communicates through that multiplexus fabric to maintain coherence, but allows models to scale in parameter count without rewriting the code. Then we have Helix R, and R stands for rack scale. It's a small half-width rack based on these images, but built from many chips in each that can be connected together. This extends that coherent memory from die to system to multi-system, and a Helix R configuration is designed to be the starting point for larger systems built on T2 or T3 silicon. The idea is that these can reach hundreds of exaflops and theoretical throughput and multiple petabytes of addressable memory. Now what stands out here is the consistency of the engineering. Each level of Helix uses the same chiplets, the same interconnect, and the same software runtime. Scaling simply becomes a question of how much silicon you assemble and where you deploy it, not how you rewrite or port workloads. This makes the product line as much a logistics framework as a silicon roadmap. In practice, this approach allows the company to build systems that overlap markets rather than simply divide them. The edge device, the rack system, and the training cluster all speak to the same architectural language. It's an unusually unified design philosophy in a market that's usually fragmented by form factor and vendor boundary. So Tsavorite has actually been running its architecture in hardware on Altera EdgeLX FPGAs. These boards demonstrate earlier versions of what the company calls the Omni Processing Unit, or OPU. It combines general-purpose ARM Neoverse v3 cores and Tsavorite's custom AI engines into one coherent domain. Each ARM core connects directly into the same fabric as the AI logic. There's no separate host CPU or PCI bridge, as orchestration and data movement all happens inside the one address space. The ARM v3 cluster runs the system software. It handles the scheduling and coordinates communication across the fabric. It can also perform some of the AI workflow if needed. The AI engines instead focus on matrix and tensor operations. Each chiplet then scales out the processing units based on performance, efficiency, and scale. The demo of these designs and FPGAs is already in the hands of customers. These AgileX-based prototypes have already executed live AI workloads, including inference and fine-tuning. They're designed to validate the coherence model, the interconnect, and the memory architecture, such that Tsavorite will implement it on silicon. It's at this point we've seen some companies even sell FPGAs with their design. But Tsavorite's own chiplets will replace FPGA logic with high-density custom silicon in 2026. Now, on top of that hardware runs the software environment, known as TAOS, the Tsavorite operating stack. TAOS is a layer that links models and frameworks to the hardware, and it controls how workload is scheduled, how memory is shared, and how compute and data flow across the fabric. The stack exposes a familiar interface so developers can use existing tools. It's compatible with CUDA and Triton, meaning most machine learning frameworks can run directly without porting. When a CUDA kernel is launched, it converts it into native instructions for the AI engines and distributes the workload automatically across all the available engines. Because every compute element sits within the same coherent memory space, the runtime doesn't need to copy data between the devices. It simply dispatches work to where the data already lives. Now, the software stack supports the full lifecycle of AI workloads. Inference, fine-tuning, and training all use the same APIs and runtime, regardless of whether the system is a Helix M, a Helix R, or a Helix D. Now, an M at the edge or an R in the data center share the same program model, only the compute performance changes, and the operating stack automatically scales with the scheduler, with the memory map, and the communication topology based on how much hardware is actually available. The Neoverse v3 cores are an important part of that structure. They handle orchestration and system management, but also act as peers in the coherence domain. This allows conventional software processes such as control logic, security, telemetry, or even lightweight inference to run on the same memory map as the AI workloads. It keeps control plane and data plane software tightly coupled and minimizes latency between management and compute. Also in the software stack, there's integrated power and thermal monitoring, so each chiplet and interconnect segment reports utilization and temperature back to the runtime. As a result, it can dynamically rebalance workloads or adjust voltage and frequency. This feedback loop maintains efficiency and reliability as systems scale to hundreds of thousands of chiplets. The runtime also provides workload isolation at the hardware level. Multiplexus can segment the memory fabric into protected regions, allowing multiple tenants to satisfy critical tasks to share resources without interfering with each other. TAOS enforces these boundaries while still treating the hardware as one unified domain for scheduling and memory management. Now, from a developer's perspective, this software stack makes the system look like a single device. Existing CUDA code runs natively, frameworks see a unified accelerator, and scaling happens on demand. The thing is, what's the go-to-market from here? Tsavorite's architecture is already in valuation with early partners, as I've said. The company reports more than $100 million in pre-orders and roughly $300 million in active design opportunities. Those span from edge to data center markets covering robotics, sensor fusion, industrial automation, and large-scale model training. These engagements roughly fall into three categories. The first is direct evaluation, where customers are running workloads on those FPGA-based prototypes. The second focuses on silicon design-ins, integrating the chiplets into partner boards and custom systems. One of the angles perhaps we didn't cover on this video is the fact that you can attach it to somebody else's silicon. It's a very valid revenue stream. The third involves full deployment of Tsavorite silicon, rack-scale configurations, delivered and supported directly by the company. Across all these programs, the company lists 8 design-ins in the works and 27 opportunities currently in qualification. In terms of timeline, pre-production systems are being finalized now, with first silicon expected in the first half of 2026, with volume ramp following later that year. Early systems will target developers and customers looking to test the platform, while additional products will extend the platform towards embedded and edge deployments as yields mature. Now, customer prototypes have already validated the coherence model, the unified memory, and the runtime. The software development kit is running live AI workloads today, allowing developers to begin optimization ahead of silicon. The company aims to start recognizing revenue by the end of 2026, matching initial hardware shipments with a stable software stack and production-level customer models. Now, to wrap this up, here's the final slide, and on the face of it, without context, it might come across as a series of buzzwords. But realistically, it's a checklist of some of the most vital areas that AI hardware is trying to solve. All four of these variables, coherence, bandwidth, modularity, and scale, are hard to solve. Tsavorite has just chosen to tackle them all in one go. In this video, I've covered each, at least at a high level. The chiplets are the physical units of compute, and the multiplexus fabric is what ties them together. The unified memory keeps the data visible across everything, and the compute clusters do the hardcore work. So that approach feels really pragmatic. I've been somewhat conflicted in chiplets since they started to be a big push. Not for the benefits I just mentioned, they've been crystal clear, but the fact that most companies using them are too stuck on monolithic paradigms and aren't taking full advantage. It feels really odd to me that companies would leave the benefits of chiplets on the table. Having a chiplet from one SKU only just doesn't make sense to me. To see it being used across a full stack in different configurations means someone here is actually smart. What Tsavorite is doing here is not new physics. It's a combination of known techniques. Cores, caches, UCIe, and a coherent interconnect, all arranged to push composability. The near-term question is whether the coherence holds at scale. Keeping hundreds of chiplets consistent under load isn't easy. Directory traffic, cache contention, and latency can all undo theoretical efficiency fast. The FPGA demos show the model works in small form. The silicon will need to prove that the same behavior carries through to rack scale. There's also the matter of software. GPUs are king so far, and any challenger has to match that ecosystem before it can claim parity on performance. The operating stack here is a path to that, offering CUDA compatibility, a unified runtime, and familiar workflows. We'll see if the mini PC approach of attracting developers is as beneficial as some of the other hardware vendors startups have shown. Overall, just to sum up here, the ingredients are sound. Modular chiplets, a consistent memory model, and a software stack that already runs. Now, we're planning to cover more of the detail of Tsavorite's design over the next couple of years to see how the engineering holds up under pressure and whether the customers actually see enough efficiency to justify the new platform. The company has promised me more detail in 2026, so stay tuned for that.